So how do we parallelize scan? Let's first start with the prefix sum problem. Once we understand that, we'll have a pattern for parallelizing any scan. By analogy to reducing an array to a single value, if we assume associativity, then we can rearrange partial sums. So somehow we want to use this idea for parallelizing scan as well. So assume associativity and consider a scan of this input array. You could try by doing the same thing you did in a reduction. For example, let's take every pair of elements and let's combine them. The result will be a new set of partial consecutive sums. For example, this node is the sum from 1 to 2, and this node is the sum from 3 to 4. In fact, let me label each intermediate sum with a notation, A colon B. The important point is that these are consecutive partial sums. So with this notation, this is what the final output should look like. So let's go back to the partial sums. Suppose you could magically and recursively do an add scan on the partial sums. That is, I take these partial sum values and I somehow magically apply a scan to them. What would I get? In this case, I would get 1 to 2 as the first scan element. Then for the second scan element, I would get 1 to 2 plus 3 to 4. In other words, 1 to 4. And for the third element, I'd get 1 to 2 plus 3 to 4 plus 5 to 6. In other words, 1 to 6. And then finally 1 to 8. Notice what that gives you. All of the even results. So voila, we've done half the work. Now what about the odd results? How do we get those? Well, that should be easy. If I want 1 to 3, I just take 1 to 2 and add 3. You can do the same thing for 1 to 5 and 1 to 7. Voila, you're done. Stop for a second and make sure that that makes sense. Now I claim here's some pseudocode that implements this scheme we just described. Let's do a quick analysis to make sure we got it right. Now here, I sub O and I sub E store the odd and even indices respectively. That is 1, 3, 5, 7, and so on, and 2, 4, 6, 8, and so on. Now this particular algorithm is in place. Adding the odd and even elements over here corresponds to this line. And by in place, I mean we take this result and we overwrite the even elements. This magic recursive step appears here, and this final combined step appears here. Now note that I've used this Python slicing notation to mean starting at element 2 and going to the end of the array. If you can convince yourself that n equals 1 produces the correct result, then you can use induction to prove that the overall algorithm is correct.